Okay, so before the break we analyzed this introductory example to particle collisions and how we could use the conservation of the form momentum vector to account for both energy and momentum conservation. So we saw that in general you would have a mass increase because of a conversion between kinetic energy and rest energy, which would be equivalent to an increase in mass. So now that you're fully refreshed after the break, I'd like to give you a little challenge. So let's say that we start now, we go the opposite way. We start with a particle with a large mass m. Which is at rest. And this disintegrates into two smaller particles, M1 and M2. And so this might look like the same scenario as here, but there's a twist. Whereas here we had identical masses of the two particles, we now allow for the masses to be different. So large particle M disintegrates into M1 and M2. So using now this framework that we just sketched for this example, this is a challenge. So assuming that the large mass is at rest to begin with, find the energies of these two particles, assuming that the masses in the problem are known. We know all the particles. We know the large m and we know the small m's. But apart from that, we know nothing about the details of the collision. We only know the masses. So find the energies E1 and E2. So we'll take 10 minutes for that and then we'll have a discussion. If someone has a proposed solution, I would be very happy if they would like to take the stage and guide us through the derivation. So it's not scary, we're 5 people here, so don't be shy. Is there anyone who would like to try? Do you have a suggested solution?
Maybe, but I haven't checked it. So.
But give it a try. We'll just discuss it as you go. So how do you get this equation?
Just have to formulate squared equals 2 squared minus m1 squared c to the 4th.
Okay.
I think.
Yeah.
And this, of course, equals
So if we could just make one comment. So from this equation for the energy, so you get E1 squared minus E2 squared is equal to M2 squared minus M1 squared.
I may have done a mistake in the.
I wonder if it should be M1 squared minus M2 squared. Do you agree?
I guess you're right about that.
Yeah. Okay.
So now, if we insert this into here
Mm-hmm.
and solve, we get E1 minus E2 equals M1 squared minus M2 squared C squared.
Mm-hmm.
So if we solve this system of equations, we get E1
All right.
That's what I got at least.
Okay. Impressive. Thank you very much. So what do you guys say? Do you agree or do you have some different result? Is John one who thinks this should be revised somehow? Okay. Well, let's try a different method to see if we can arrive at the same result. So this was very elegantly executed. I can see, okay, yeah.
There's a little mistake up in the leftmost equation.
Mm-hmm. This one?
Yes.
Okay. Oh, should be like this?
Yes.
Right, okay. I don't think that has any consequence for this result. No, but you're right, it should be a square. Okay, so let's see. I'm going to propose a slightly different method, but let's see if we can get the same result. So just like you did, I defined the 4 vectors before and after. So we have this. And what I would like to do as sort of the main equation for deriving this is to use the invariance of these 4 momentum vectors. So I know that the scalar product of the 4 momentum vectors should be an invariant. And from this equation then, before and after, I get that this should be the case. All right, so this form momentum after the collision we should be able to write as the sum of the form momentum vectors of each particle, 1 and 2. So P2 mu, the form momentum vector for particle 2, is equal to the total form momentum vector minus P1 mu. Now, the invariance of the form momentum vector not only applies to the total form momentum vector, but it also applies individually to each of the form momentum particle of the particles. So P2 mu should be equal to this. And if I now combine 1 and 2, I get the following. Okay, now these vectors we know. So we can evaluate this right-hand side. So this is just writing out the square. And so using the invariance of each of these form momentum vectors, we get that this first one should just be minus large m squared, c squared. Second one is given like this, the mass associated with particle 1. And this final term, we have to check then. So we have this for p mu, and then we have this. Now, fortunately, this component here of the momentum is 0 for the initial particle. So we only get a contribution from the product between the fourth components. So we should get plus 2m E1. So the minus sign cancels the I squared. So now we have an equation which we can rewrite as this. And if we compare it with this equation here, we see that we have full agreement. Now I could derive this result for E2 by considering the square of P1 mu instead. But I could also argue from symmetry reasons that I should be able to obtain E2 simply by interchanging the masses here. So we should have this, which agrees with this equation here. So you were absolutely right. Thanks for sharing your derivation. And I'm not sure, I think this was more elegant than what I had in mind here, but at least it shows you that you can do this in several ways. Oh, by the way, we can just make a note here that in the special case where these two masses are equal, we obtain here that each of the energies is given as half of the initial rest energy. And I guess that seems reasonable because if you have identical particles in the final product, well then there's no reason for why they shouldn't split the energy evenly between them. But it's important to note here that M is not necessarily equal to the sum of these two masses. This was, as we saw, because kinetic energy can be, or rest energy even, can be converted to kinetic energy. Well, there is in fact at least a third route that we could have used to arrive at this result. This particular route could perhaps be even more convenient if we were particularly interested in the velocities of the particles as well. So what we could have done then is just write down the equations for the conservation of the four momentum vector. So in that case, we would have just considered the conservation of P mu. That will give us the following equation from the fourth component of the four momentum vector. So the fourth component here is just IMC, and the fourth component of each of the four momentum vectors for particles 1 and 2 are IE1 and 2 over C. But we also know that these energies can be written in the following way, where this now combines both the rest energy and the kinetic energy. So note that I've attached the J index indicating which particle we have, 1 or 2, not only to the mass, but also to the gamma factor, to consider that in general the velocities might be different. And in fact, if the masses are different, the velocities have to be different. Because if we're supposed to be in the center of mass system, and the particles have different mass, well, the velocities also have to be different to get total momentum equals 0. So that will be one equation, and that will be my second equation, which states that the momentum, the 3 momentum, should be conserved. So this equation comes from the fourth component, and this from the 3 first. So I've used absolute value sign here to indicate that V1 and V2 should in general have opposite signs, because they have to propagate in opposite directions to have a total momentum of 0. Oh, sorry, it should be 1 and 2 here. So from these equations, we now have an equation system for the velocities V1 and V2. So from this, we should be able to solve we should be able to solve for v1 and v2, the resulting velocities, as functions of the masses in the system. Now, the derivation would probably be a whole lot messier than the two methods we used here, because we have a couple of complicating factors. We have a root here, one of the root 1 minus beta squared, and here we have an absolute value sign, so we have to be a bit careful about taking into account the appropriate signs and everything like that. But in principle, it should be doable. So, and once we have v1 and v2, we could find the energies of the particles precisely via this relation. So there are many ways we could arrive at the final result. I just wanted to show you several alternatives. All right. So far, we've been considering pretty nice situations. We've had either one particle disintegrating into two particles or two particles colliding, creating one particle. But now we're going to up the ante quite a lot, actually. And consider the following. Oops. So this is a bit more complicated. We now have two particles colliding, but now we have, in the after situation, a whole bunch of particles in general, which all have different masses and different momenta. So we have at hand a situation where two particles collide or interact in a way such that n new particles are created, which in general may have different masses. Now at first sight, this might seem as a formidable problem. So consider the fact that we know nothing about the details in the aftermath of this collision. It's impossible to analyze exactly how these particles, well, not impossible, but it's very hard to analyze how these particles, for instance, exit with respect to each other right after the collision and how they sort of move. So the only thing we know is that two particles collide and particles are created. But we know nothing about the details. So what could we possibly say? How could we possibly analyze such a complicated situation? Well, it turns out that via this relativistic framework, just using classical mechanics, we can actually say some useful things about this type of situation. So we assume here that what we do know is what happens at t equals 0, which we can define as right before the collision, and at t goes to infinity, which we here define as sufficiently long time after the collision. Now, based on our previous experience with these two examples, we've seen that the center of mass system has been very advantageous in order to analyze or to do the analytical calculations. So we'll try with the same here. Let's start out by considering the center of mass system. So again, energy and momentum conservation are jointly expressed through the conservation of the total form momentum. Perhaps I should insert that. So, at t equals 0, or right before the collision, this is the total form momentum. And as t goes towards infinity, or put into words, sufficiently long time after the collision, we have this, where each of these form momenta have their general definition like this. Okay, so this is what we know, and we're armed with two very important things. One thing is that the form momentum is conserved. So p mu is equal to p mu prime. And the other thing we know is that the scalar product of this total form momentum vector is an invariant. So in the center of mass system, we have this. Again, due to the convenient fact that the total momentum is equal to 0. Now we do know that this is an invariant quantity, and if you have the form momentum p mu of some particle, then it's squaring this 4 vector gives you this in general. And hence, we should be able to, at least for notation, Sorry. Should be able to write it like this. So p mu prime squared should be equal to an invariant, which we define like this. And in the center of mass system, this invariant is expressed via the energy. Can we say something about this m, which I've called the equivalent mass of the system? Or more precisely, can we say something about large m in terms of the masses of these particles? So let me try to make a statement here. I'm proposing here that the equivalent mass of the system is equal to the sum of all the masses of the particles after the collision. Would you say that this is true or false? I see we're a bit in overtime, so you'll get the answer next time.